How about a grand tour? Not of continents, but of science. Let's seek truth where it may change. Time, matter, energy, universe, earth, life, brain, mind. The cosmic spectrum of science. What discoveries lie ahead? What surprises are in store? What breakthroughs could make the largest impact? We get the big story about the structure of matter and energy, the beginnings and ends of the universe, the global changes on our planet, the development of life, and the essence of brain and mind. Next, on Closer to Truth, what are the great questions of science? Welcome to Closer to Truth. I'm Robert Kuhn. Great science requires great questions. So for this program, we've brought together 5 world-renowned scientists and thinkers, and we've asked them to make a list. Dr. Steve Koonin is Vice President and Provost of Caltech, where he is Professor of Theoretical Physics. Dr. Neil deGrasse Tyson, an astrophysicist at Princeton, is Director of the Hayden Planetarium of the American Museum of Natural History. Timothy Ferris is an award-winning author of science books and a consultant to NASA on long-term space policy. Dr. Francisco Ayala, Professor of Biology and Philosophy at the University of California at Irvine, is called the Renaissance man of evolutionary biology. And Dr. Patricia Churchland is Professor of Philosophy at the University of California at San Diego, where she focuses on neuroscience. Steve, as Provost of Caltech, one of the world's great scientific organizations, of course, you are responsible for all of its research. Do great questions drive great scientists?
Yes, I think they do, Robert. You know, science is about figuring out how the world works. And there are really 2 kinds of science. One is where you kind of know the rules, but you're figuring out how they apply in some specific situation. And then there's another kind of science where you're really trying to figure out the rules themselves, all right? And so there have been revolutions, thermodynamics, quantum mechanics, relativity, understanding the genetic code, for example, that really changed the whole game. And, you know, my late colleague Dick Feynman used to say, once you know the rules, everything else is just chess. And so it is figuring out those rules, I think, that are really the great questions of the universe.
What I find interesting about your own research is it ranges so broadly from computational nuclear physics to global change on the planet. What drives you?
Gee, what does drive me? That's it. I think interesting questions and the possibility of being able to answer those questions. You can't ask questions that are too far out there. You want to try to really
solvable
pick questions that you can solve.
Good. We'll get to some of them. Okay. Neil, you are what I'd call a public scientist in a grand tradition, a professor of astrophysics at Princeton and director of the Hayden Planetarium, which many of us got our first exposure to the universe. And his
my first night sky.
Right, very terrific. Why are the grand questions of science important for the public?
Well, not all scientists ever have the privilege of answering alone the grand questions of science, but it's the grand questions that are the carrot, the intellectual carrot that's put out there that actually seduce people to wanting to do science in the first place, and they keep you going all throughout the journey. And often the fun of doing science is not even answering that great question, but it's the path you take along the way. And it's that path that gets you closer to the machinery of how the world works.
And that great question's always out there.
The great questions, and once you solve that, there's going to be another question on the other side of it. So don't be fooled by how close you are. Yeah.
We'll get to that too. Tim, you're a journalist, a superb writer of elegant and insightful books on astronomy, such as The Whole Shebang. Why do you think so many of these great questions skew to physics and astronomy?
Well, physics because it looks at the foundations, the very smallest things, and astronomy because it looks at the other end of the scale, the very largest. And within that framework is every phenomenon that we know about and that we are.
Francisco, I need your help. And Pat, I feel like I'm surrounded by astronomers and physicists and astronomy. Let's have a little bit of biology here. Why is it now that people, when they're asking great questions, are now making more of in the direction of biology?
Because the major breakthrough only happened in the 19th century. Only after Darwin can we ask the fundamental questions of biology. Before that, birds have wings and we have lungs, but there was no explanation for that. And they were attributed to the creator. Since Darwin, we have been able to ask all the important questions as to where we come from, why we work the way we work, our bodies, and everything else, and how we relate to each other.
And as time is going on, more and more of these questions are biologically based.
Absolutely. And of course, after all, biology deals with living organisms, which, with all due respect to all the physicists and astronomers, are the most interesting and the most diversified things in the world. So we have there a field to study and to investigate for a long time.
Pat, you're one of the leading thinkers about the brain-mind, traditionally called the mind-body problem. Though I'm expressing my own prejudice early, tell me why the brain and the mind must be among the great questions of science.
Well, I think there are a number of different questions that we want to separate here. One question has to do with whether psychological states, our mental life, remembering, thinking, creating, whether that is really a subset of brain activity or not. And on that major question, I think, although there are residual problems, I think largely people agree that it is only the brain, that there isn't anything in addition to the brain, such as a non-physical soul.
I say some people agree with that.
I think by and large scientists do, and I think that's really the way the evidence stacks up now in neuroscience. It's possible that there is a non-physical soul, but it doesn't really look like that's the way things work. But the other sort of major question that you want to ask, given that framework then, is how is it that high-level psychological effects come about from basic neural effects? How is it that you've got these cells organized in this complex way and they give rise to my seeing motion or my seeing color or my smelling a rose? And I think that those are the questions that certainly preoccupy me at this stage.
Right. Well, we want to get to that later, but let's start at the fundamental aspects. Remember what we're going to do. We're going to go through this category. We're going to do physics, astronomy, Earth, life, including evolution, and then brain and mind. So I want to start with physics. What are the great questions of physics? I want to start with Steve.
Well, I think there are several interesting questions right now at the forefront. One is we have a picture of the physical world called the Standard Model. It's got quarks, it's got leptons in it, it's got gauge bosons. And the question,
quarks being the most fundamental part?
Well, together with the leptons, that's right, being the most fundamental parts of matter. And the question is, to what extent is that Standard Model valid? So far, it has proven maddeningly valid. Everywhere we look to test it, it seems to be right. But it's got some free parameters in it, some things that we have to go out and measure. What are the values of the fine structure constant, for example? We would like to know how many free parameters are there, what are those values, and are they all related in some way?
Tim, you have looked at quantum questions in physics. Tell us about those.
Well, physics in the end of the 20th century is comprised of quantum physics and relativity, and as we've alluded to a little bit here, they're not quite compatible, and there are aspects of the quantum world that are very challenging, difficult to understand. And amongst physicists that I've talked to, some feel that these questions won't ever be of any functional importance.
Other than the show.
Other than this. And others feel that that through this keyhole, there may be a great deal to be seen. If you look at the whole universe in quantum terms, it's quite interesting to think about light traveling all these distances and then striking your eye and suddenly turning into something different, a kind of knowledge or perception. And when we try to understand the two ends of the spectrum, the questions naturally arise, and to me they're equally important questions, of how did the whole thing originate, how did the universe originate, and how did human intelligence originate to complete this loop?
Well, that's what all these questions are. They are indeed a loop or a hierarchy. I like loop better than hierarchy, and we started physics with the universe, and we'll end with the brain. Neil, you've looked at philosophically the Copernican principle as it relates to physics. Tell us a little about that.
Well, we've known since Copernicus that Just to remind people, Copernicus sort of restored the sun as the center of the then known universe, previously understood or believed to be Earth. And that dislodged human perception of ourselves and our own importance and made it just one of many other planets, a family of planets in the solar system. And then moving onward, we then learn that the sun is not the center of the galaxy. It's just one of billions, hundreds of billions of stars in a galaxy, which is one of perhaps 100 billion other galaxies. And so cosmic discovery has been this long, many steps towards demonstrating that anytime we thought we were special, we're in fact not.
Do you think there's a limit to that?
No, actually. I think that'll just continue. I mean, even to the very chemistry of our bodies, the fact that we're carbon-based life. Carbon is one of the most abundant elements in the galaxy.
Formed in the crucible of...
Formed in the crucible of high-mass stars that then exploded and spread their guts across the galaxy. All this stuff that makes planets and life and people. And so the commonality, and by the way, this is quite a testament to the universality of the laws of physics. Without that, we'd have nothing to study. If in this room at this moment in time, the laws of physics were one thing, and then there was something random 10 minutes from now, we'd all be out of a job.
That's a fundamental principle of science.
It's a fundamental principle, but we don't just wish it were true. Evidence has demonstrated throughout eons that it is.
What has happened here, and this is very important, is that we have merged seamlessly from the questions of physics to the questions of astrophysics and origins.
I think that's a trend that's going to continue.
And that is a fundamental trend of what's happened in science over the last 30 years. And that's very exciting. You can't talk about fundamental physics without talking about origin of the universe, and you certainly can't do the reverse.
Part of the reason is that we can't get to the scales of fundamental physics unless we look out in the universe. We look back toward the Big Bang. We don't have powerful enough accelerators.
Right, and never can.
That's right.
And I think that biology and neuroscience and are increasingly going to be implicated in these questions too. I mean, biology started out existing, as it were, on a tabletop on a planet in a wider context about which very little was known. I think the future of biology will involve looking at different environments on other planets and trying to figure out to what extent are the way things are on this living planet accidents, and to what degree could they only be this way?
Why would that be interesting? I'm much more interested in understanding life in this planet. And I know that we are not accidents. I know that we are not predestined either.
Wouldn't you be
I'm not so interested in what is happening out there, not at first.
But wouldn't you be interested in knowing whether evolution, for instance, is a universal law or a law peculiar to this one planet?
Well, I'm not particularly interested in that issue. I'm much more interested in issues that as I will bring up later, that the very interesting evolutionary questions right there.
So if we had another instance of life somewhere else, if we found it a different chemistry, for example, different body structure, cell structure, wouldn't it be so interesting?
Oh, it will be interesting, but I have many more interesting questions right here.
But however,
on this planet.
You can't neglect the fact that, and I bring by analogy our study of the solar system. For the longest time, we only knew of the 8 or 9 planets in our own solar system, so theorists come up with models that explain why you have a big planet here and a small planet here and rings here and icy objects there, and you construct your whole paradigm based on an example of one. And that can be so limiting when just by looking over the other side of the fence, and we haven't found life elsewhere, but the fact that you have another example, we have other solar systems out there that now a whole new field is born called comparative planetology.
Francisco?
Neil, but that's the difference, precisely. You deal with relatively simple systems that can be repeated. Organisms don't get repeated. I don't expect to find human beings or intelligent life anywhere in the universe.
But don't you think you
I
could
have enough
sharpen your
diversity right here, and I want to understand what is happening here. I have all my universe, as many as I want for now, on this planet.
Let's stay on the universe. We've talked about life. I want to talk about some other things like the expansion of the universe. This is a great question. Neil, tell us about what's happening with the expansion.
Well, we're expanding, and we've been expanding. And it looks like it's a one-way trip. For the longest while, theorists felt philosophically that a better universe would be one in which we would expand and recollapse and then expand again, because that took away the worrisome issue of whether there was only ever one beginning to the universe. But it looks like we're on a one-way trip.
And it's accelerating.
Recent evidence shows that it's not only expanding, it's accelerating. So, and the temperature of the universe is dropping, the density of matter is becoming less and less, and we're headed to what we call a thermal death, where everything is the same temperature, and that temperature would be very cold, close to absolute zero.
Tim, take us in a more
That's
complex...
in a few hundred billion years.
I'm not worried. The show's only 30 minutes. Take us in a more complex version of this, because the new theories of inflation, chaotic inflation, multi-universes, it's a whole other realm of reality.
In the original models of the Big Bang, when the expansion of the universe had been first discovered, there was never an explanation as to why the universe should be expanding in the first place. The inflationary model derives from finding physically plausible mechanisms that could cause space itself to expand, and that's what's going on in the expanding universe. It's space itself that's expanding. In these models, the universe began as a bubble, and the models solve a lot of problems for cosmology. They're very beautiful, but they do seem to imply that the bubble occurred in a pre-existing space of some sort. And this raises the, to me, marvelously stimulating notion of there being ensembles of many universes, of which ours is one example. In that case, a question similar to the biological question of chance and necessity, as Jacques Monod called it, arises in cosmology. What aspects of our universe are here by chance, and which ones had to be the way they are because of the only logical possible outcome?
Let's go to biology quickly. We talked about it before in terms of exobiology, but right here on Earth, what's happening with understanding the human genome and the full analysis of what we are as human beings?
The genome gives us something very interesting and important, but it's just the very beginning. Take the point of the genome being linearly organized molecule, and then you have a being, a human being, or any other kind of organism, which is four-dimensional. You know, you have a body and which lives in time. How do we go from those instructions to the organism? That's one of the fundamental questions.
The linear structure of our genetic material.
The information there is like the sequence of letters in a sentence of English. You have the sentence, you read it, but now you have to go from there to create the organism. And that's where the interesting biology comes.
Pat, take us to the highest level with brain and mind. What are some of the core questions of neuroscience that you're looking at for the next, into the future?
Well, you know, the thing to remember about neuroscience, and in this it really differs from physics, from astronomy, and even parts, I think, of cell biology, and that is that in neuroscience we don't yet have what you might call an explanatory framework. Neuroscience is still very, very young. We don't have the strong paradigms that are established within which we can see how the general explanations go. Now, that makes it very exciting, but it also means that we can't expect from neuroscience the kinds of things that you can expect from physics.
What are some of the fundamental questions, like learning and emotion?
Well, I'd like to think about it in a slightly different way. I mean, of course, there are all those kinds of questions as well, but it's important to realize that you first of all have to know what the basic structural bits are. And it looks like neurons are those basic structural bits.
Those are nerve cells in the brain.
And those are cells. But there's many things that we don't really understand about the single cell. And in particular, and this I think comes as a surprise when we contemplate the larger questions such as the nature of consciousness and the biological mechanisms for decision making, we still have not really satisfactorily answered the question of how individual neurons work. In particular, we don't know how neurons code information.
Steve, are there any grand questions about Earth?
Sure. I think there are questions, for example, about the fluid Earth, the ocean, and the atmospheres. What is the extent of the natural variability of the climate system? What causes that variability? What makes the ice ages, for example? We don't understand those questions yet. Similarly, the deep oceans are a very important component of the Earth atmosphere system, and we don't really understand what's going on in the deep ocean.
And that affects everything?
That affects the long-term climate on the Earth, which is obviously of great interest to us.
Well, we don't even know where the oceans came from.
That's certainly true also. Where did the water come from?
Yeah.
Right?
Sounds like we're in the third grade. You know where the water came from?
Yeah, well, I know a place where it could have come from. We've got comets streaming throughout the solar system, and they got tons of water in them. And that's one way we could have brought much of the oceans. There's some problems with some isotope ratios that still are unresolved. But I beg to differ that questions related to Earth are in the category of the big questions because Earth is just one planet. And when I think of big questions, I think of questions that apply everywhere to the future evolution of the entire universe.
If you had a glacier coming down against New York, you think it's a
that's
big
right.
question.
Don't get me wrong. I love, Earth. That's our planet. You know, I like Earth.
let me give you one that is in fact generic, and that's the origin of magnetic fields in planets.
Good,
Okay?
there you go.
Some planets have magnetic fields, others don't. The Earth's magnetic field reverses every 100,000 years or something like that. We don't
Yes.
understand how that happens.
That's right. There you go.
There's a big question,
There
all
you
right?
go.
But I still think the climate is a grand question because we really care about the answer.
I guess what I try to do is I would think of it not so much as climate challenges on Earth, but generalizing it to planetary climates.
Yeah.
And why does Jupiter's red spot survive? Why does it survive for 300 years?
Sure, but you may get very different answers on different planets. It's going to be like biology, that there's a different answer in each system.
You'd hope not, but that's something itself to know if
Yeah,
in fact it requires a different explanation.
Francisco, let's go to biology. What are some of the grand questions we haven't touched upon?
I would say there are three great questions in biology. The ape-human transformation, the gene-soma transformation,
From genes to cells.
and the brain-mind transformation. What I mean by the ape-human transformation is why is it that we are so similar to the apes, and yet something went differently in human evolution that gave us what we are. Again, our culture, our mind. By the gene-soma transformation, I mean something to which we alluded earlier. How is it that the linear information in the genetic code becomes transformed into an organism which is so complex, with many different parts interacted in many different ways and changing through life? And for the brain-mind transformation, I think Pat can answer much better than I.
As I've been listening to this, I was struck by a thought that hadn't occurred to me before, which is that two of these great questions are quite closely related, aren't they? They involve code. They involve encryption. One of them is the question that you raised of how it works that a genetic code, which is simply a code, can manifest itself as such complex and very living organisms. What makes that connection? And it occurs to me that this is also the issue of intelligence. In searching for extraterrestrial intelligence, we define intelligence pragmatically as the ability to send an encoded message. We're the only species on Earth, and probably in the history of the Earth, that's had that ability.
What remains to be done right now is to ask a final question. I want to ask everybody to think about this. If you could get the absolute answer to one great question, but only one, which one is it going to be? Short answer, Steve.
How did life begin, and is there life elsewhere in the universe?
Well, it's two questions, but it's all right.
I'd like to know how intelligence originated, because until I know that, I don't know whether Francisco is right in assuming that intelligence is rare in the cosmos.
Francisco?
I would be interested more than anything else in Pat's question, the ultimate question that she was referring to, the brain-mind transformation. How out of all these neurons and all the chemicals that are going back and forth and electrical signals, I get a unitary mind, and also a mind that can think and write poetry, can listen to music, and have conversations like this.
Especially that. Yeah.
He stole my question. I do agree with Francisco. I think that understanding how out of meat you can get thought.
Hey, leave it there.
Perception.
That's poetry.
All right. That's the grand question.
There's some questions I don't want to risk wasting my question on because they may be dead ends. But the one that's not a dead end is, what is the nature and overall properties of dark matter in the universe, which is ubiquitous. We are dumb stupid about it. We don't know we know it's there because everything feels its gravity, but nothing else about it
And
can be
there's
felt.
more of it than what we can see.
There's more of it than all the kind of matter we know that we're made of. So that's the frontier.
I don't know how you feel, but I'm exhausted. The great questions of science take us into the realms of curiosity, creativity, intellectual rigor, speculation, and even fantasy. We embrace subatomic structure and envision multi-universe inflation. We witness the incredible diversity of biology and reach up to the human brain, the most complex piece of matter in the cosmos. For me, it's thrilling to skim the bits and pieces of heroic thinking. It puts one's own life into perspective. And whether grand design or random accident, it makes you realize how connected we all are. From consciousness to cosmology, what a privilege to get closer to truth. I'm Robert Kuhn.
To explore topics like these, join us online at www.closertotruth.com.